So let us do that. So we want to talk about simplicial complexes. The name itself is pretty intuitive. It says that we want to build a complex out of simplices. So it's like, building a tower of simplices and so on. I mean, think of this why they're called shopping complexes, right? So you have these shops from where you shop on, and you are building those shops on the top of each other. Some shop is left to the other, some shop is right to your shop and stuff. So there's this thing called this complex, and the simplicial complexes is just that you are taking simplices and you are building a you are constructing another figure or another complex out of them. That's what this simplicial complex means intuitively. So now let's get to the mathematical definition. Is that let K be a set of finite number of simplices or simplexes in Rm. Be a finite, let be a set of finite number of simplexes in Rm, then K is called a simplicial complex if the following conditions are satisfied. Condition number 1 is that an arbitrary face of a simplex of K belongs to K. That is, if I have a face that belongs to K, and I'm calling this face with a sigma. Now you may get confused that, okay, I used to denote simplices with sigma, right? But then when we talked about faces, we said that, okay, so you have a three-dimensional or three simplices, three simplex, let's say, but that three simplex also contains two simplexes. So those two simplexes were the face of that three simplex, right? So that's why I wrote this sigma, that it's a face that belongs to this K, and sigma prime equal less than sigma. If that's the case, that is this, and if this is the case, then sigma prime also belongs to K. This is one condition. And the other condition is that if sigma and sigma prime belong to K, then either sigma intersection with sigma prime is null, that means empty, they don't have any common region, so to say, or sigma intersected with sigma prime is equal less than sigma, and sigma intersected with sigma prime is equal less than sigma prime. So what does this mean? This condition looks a bit weird mathematically, but let me give you an example that will clear out what are these conditions. So the second condition tells you, the first condition is pretty easy to see, right? But the second condition says that, okay, so I have two faces, then if I have these two faces, that is a part of a simplical complex, okay, then those two faces either their intersection is null or their intersection is either of the faces. It can be either sigma or sigma prime. Okay, so let's take a visual example to understand this. Let's have, so this is the example to understand this. So let's say I have a filled in triangle like this. I have a hollow triangle that is attached with it, and let's say this is P0, P1, P2, P3. Now I have another simplex over here that is connected with P2. Let's say this is P4, like this. You can see that if you take any of the faces, the first condition is easily satisfied over here. But if you look at the second condition, then you can take any n face or any r face, that is, you can take any one face, two face, sort of things like that, and you can check easily from this drawing that none of the faces intersect each other, right? That means their intersection is null. However, so this can be, what can be, this is a k, or so to say, a simplicial complex. Okay, but now if I draw the same thing again, but this time P0, P1, P2, P3, now let's say this is P4. Now I do something like this. I connect it with P1 like this. Okay, this is not a simplicial complex. Why? Because just look at the second condition. What does it say? That either your faces don't intersect with each other, that means their intersection is null, or their intersection must be one of the faces, right? But look at this guy over here. It intersects with this P2, P3 face, which is a one face or a one-dimensional face. But their intersection point over here, intuitively, it's not a face of this simplex, or so to say, this this simplex. So that's why, because of this intersection is not null, and at the same time this intersection point is not a face of this simplex or this complex, whatever you want to call it, this is not a simplicial complex. Okay, so that's what the second condition means. And how now we want to look at an example. How does a K look? Okay, so this is an example of the simplicial complex. Let's say my sigma is P1, P2, P3, which is, again, if I take a filled in triangle like this one, let's say P1, P2, P3, like this, then my simplicial complex that is a set K is denoted by P1, P2, P3, P1, P2, P2, P3, P3, P1, and since I filled it in, I'll also have this P1, P2, and P3 base. And this is similar to something we showed earlier over here, this guy. So in some sense you are just taking a set of faces. That means when we talked about the faces, I said, oh, let me define a set of faces that looks like this, a collection of faces. And now you see that the simplicial complex is just defined in such a way that it will produce the same thing. But this is the actual mathematical definition of a simplicial complex. So you have a structure, you're calling it a complex, and this structure is built out of different simplices. So technically, or in summary, we say that a simplicial complex is a set whose elements are simplexes. Okay.